Welcome to this presentation on stoichiometry, one of the funkiest words in chemistry. But before we begin to decode what it actually means, I want to take a quick look at the chemical equation. Now, you've all probably seen hundreds of chemical equations in your chemistry course already, so this is probably just going to be a little bit of review. And in this chemical equation, we've got some elemental magnesium, we're adding it to some elemental fluorine, and we're getting an ionic compound, magnesium fluoride. Simple enough. And we all know that whatever we have on the left side of our chemical equation, these are called reactants. These are called reactants. And these are the things that we begin with. These are the things we add to our test tube or we add to our mixture to begin the chemical reaction, hence the term reactants. And why do we want to start a chemical reaction? Well, we want to produce something. And what do we produce? Well, we produce products. We produce products, or in this case, just a product. That product being magnesium fluoride. And so this is simple enough. We've got reactants. This yield sign indicates that these reactants produce some product, and this here is our product. But there's something wrong with this chemical equation. There's something wrong with this chemical equation. We know, according to Dalton, that chemical reactions are just the rearrangement of atoms in different structures, and we know that atoms can neither be created nor destroyed. So what we've got on the left-hand side of the equation has to equal what we have on the right-hand side of the equation. They can be contained within different substances, but we have to have the same number and the same kinds of atoms on both sides of the equation. Let's see if that holds true. Well, we've got one magnesium over here, and that one magnesium pops up over here. We've only got one fluorine over here, but we've got two fluorines over here. So we can't just produce one fluorine out of the ether. So we have to do something to this equation. What we do is we balance this chemical equation. And to do that, all we're going to do is add a coefficient of 2, in front of that fluorine to indicate that in this reaction, say at the atomic level, for every one atom of magnesium, we need to have 2 atoms of fluorine to produce 1 formula unit of magnesium fluoride. And whenever we don't have a coefficient in front of some symbol, we assume that that coefficient is a 1. So we've got 1 atom of magnesium to 2 atoms of fluorine. We can also think about this in terms of moles. We can say 1 mole of magnesium combines with 2 moles of fluorine to produce 1 mole of magnesium fluoride. And the last thing to say about this chemical equation, we're going to talk about briefly these little parenthetical letters. What do these actually mean? Well, you probably know these are just state symbols. And when I say state symbols, it probably makes more sense why we have an S and a G here. Magnesium, elemental magnesium, is a solid. That's what the S stands for. Elemental fluorine is a gas. That's why we have a G here. And the substance magnesium fluoride is a solid, so we've got an S. And we can have 2 other state symbols. We can have L, which stands for liquid, or we can have AQ, which stands for aqueous. And an aqueous solution is just dissolved in water, but we'll look at that in more detail in future videos. But let's take a closer look at balancing chemical equations and maybe develop some strategies to do so. It's not too difficult, but we'll use this relatively simple example to take a first look. And in this chemical equation, we've got some ammonia gas added to some oxygen gas, produces nitrogen oxide gas, and some water vapor. Simple enough. Now, the way I like to go about balancing chemical equations is I like to start from the left-hand side and look at each individual element and work my way to the right-hand side from reactants to products. So let's begin with ammonia right here and just count up what kind of atoms we have. Well, we've got one nitrogen right here, and 3 hydrogens. 3 hydrogens. Now let's see if we have the same number over here. Well, we've got 1 nitrogen in this NO, so that works. We've got a check mark there. But we've got, let's see, we've got only 2 hydrogens. 2 hydrogens, so 1 nitrogen and 2 hydrogens. But we need the same number of hydrogens on both sides. So what are we going to do? Well, because this isn't a simple 2-to-1 ratio, it's a non-integer ratio, what we're going to do is multiply the left-hand side by this number 2, this ammonia, and multiply this water by 3. And what's that going to do? We're going to put a 2 here and put a 3 here. So we're going to end up with no longer 3 hydrogens, but 6 hydrogens. And similarly, 2 times 3, 6 hydrogens over here. But we also have to remember that because we put a 2 in front of the ammonia, we now have 2 nitrogens. We now have 2 nitrogens on the left-hand side, which means we also need 2 nitrogens on the right-hand side. So we're going to multiply this NO here by 2 as well to give us 2 nitrogens. Now things get a little bit tricky. Let's look at oxygen. So we've got 2 oxygens to begin with on the reactant side. On the product side, because of these new coefficients of 2 and 3, we've got 2 oxygens here and 3 oxygens here, so we've got 5 oxygens total. And how are we going to reconcile this? Well, what I suggest you do is for this last coefficient, if you need to multiply by 2 different numbers, so you might think we multiply this side by 5 and this side by 2, I suggest you actually write a 5 halves here. Because you think about it like this, 5 halves times O2 is going to give us 5 molecules of oxygen. Excuse me, 5 atoms of oxygen. Molecules are covalent compounds. 5 atoms of oxygen, and that would also give us 5 over here. So on the surface, this equation looks balanced. The problem is, we don't like fractions when we balance chemical equations. We want whole numbers. We want whole numbers. And so what we do at this point is to get rid of this 5 halves, we're going to multiply everything in this chemical equation by the denominator in this fraction. So that denominator is 2. So we're going to multiply everything by 2. So this 2 becomes a 4, this 5 halves becomes a 5, this 2 becomes a 4, and this 3 becomes a 6. And now we can't reduce this anymore because although these 4, 4, and 6 are all divisible by 2, 5 is not divisible by 2. And so these are the lowest ratios we can have, and now we've balanced our chemical equation. We've got 4 nitrogens on both sides, we've got, let's see, 12 hydrogens, and we've got 10 oxygens on each side. So that works out. And so now that we know how to balance chemical equations, we can take a look at the study of stoichiometry. And stoichiometry is essentially just a study of measuring the relative numbers of products and reactants in a chemical equation. If I give you if I say we start out with a certain number of reactants, can you tell me how many products we produce in our chemical reaction? That's what stoichiometry is all about. And again, as we do so often, I want to take a look at stoichiometry by looking at a quick example. And our example here is going to be this chemical reaction, this chemical equation, which I've already balanced for you. So lithium hydroxide plus some carbon dioxide is going to produce some lithium carbonate and some liquid water. My question for you is how much lithium carbonate can we make if I say we start out with 20 grams of lithium hydroxide and 15 grams, let's say 15 grams of carbon dioxide. How do we begin with this problem? The first thing we're going to do is we want to convert these numbers to moles. We don't really want to work at the atomic level because, of course, there are so many atoms in 20 grams of lithium hydroxide and so many molecules of carbon dioxide in 15 grams. So we're going to work with moles. So the first step, convert to moles. Convert to moles. We want to figure out how many moles of reactants we're beginning with. And to do that, we're going to need to figure out the molar mass, as we've done in previous videos, of our 2 reactants. Lithium hydroxide, we're just going to add the molar mass of lithium, which is 6.94, plus the molar mass of oxygen, 16.00, hydrogen 1.01, and we're going to get the molar mass of lithium hydroxide is roughly 23.95 grams per mole. Remember, to get the number of moles you have, given the amount of mass, you just divide that mass by the molar mass, and then our units are going to cancel nicely. Moles is going to come up to the numerator, and we're going to get something like, to 2 significant figures, 0.84 moles. I forgot to mention that this 20 here, this is 2 significant figures. So 0.84 moles. Now we can do the same thing with our carbon dioxide. Carbon dioxide, our molar mass for carbon dioxide is going to be 12.01, the molar mass of carbon, plus 2 times the molar mass of oxygen, which is 16. Nice even number. And that's going to equal 44.01 grams per mole. We do exactly the same thing we did for lithium hydroxide. We're going to divide, how many grams did I say we had? 15 grams. 15 grams of carbon dioxide. Divide that by 44.01 grams per mole. If you ever forget how to do this, you can just think about the units. We always want to cancel grams and bring moles up top, so we divide by the molar mass. And this is going to give us something like 0.34 moles. Okay, where do we go from here? Well, let's look at the coefficients in our chemical equation. We see that lithium hydroxide has a 2 in front of it, and carbon dioxide doesn't have anything, so we assume there's a 1. This means that for every one molecule of carbon dioxide, we need 2 formula units, lithium hydroxide, or from a molar perspective, for every 1 mole of carbon dioxide, we need 2 moles of lithium hydroxide. And so we could say that the ratio, our ratio of lithium hydroxide to carbon dioxide is 2 to 1. 2 to 1. Now let's see how our actual amounts of reactants compare to this. Well, we've got 0.84 moles of lithium hydroxide, 0.84 moles, and we've got 0.34 moles of carbon dioxide. What does this come out to? This comes out to 2.47. This shouldn't be an equal sign. We should just be comparing these two numbers. And so it looks like we've actually got a higher proportion of lithium hydroxide to carbon dioxide than our chemical equation indicates. Now, can we just consume both or all of these quantities? Can we consume 0.84 moles of lithium hydroxide and 0.34 moles of carbon dioxide? Well, no, we can't, because we can only consume twice the amount of lithium hydroxide as we do carbon dioxide. If we use up all the carbon dioxide, we're only going to be using 2 times this amount of lithium hydroxide. So we can only use 0.68 moles of lithium hydroxide will be used, which means we're going to have some lithium hydroxide left over that won't be converted to lithium carbonate, won't be consumed in our chemical reaction. And this process is called limiting the chemical reaction. But what actually limits the chemical reaction? Well, it's our amount of carbon dioxide. We don't have enough carbon dioxide to react with 0.84 moles of lithium hydroxide. And so we call carbon dioxide in this chemical reaction the limiting reactant. Limiting reactant. So in our chemical reaction, we're going to consume 0.34 moles of carbon dioxide and 0.68 moles of lithium hydroxide. The remaining amount of lithium hydroxide is just going to sit there and be dormant. It's going to do absolutely nothing. What was our original question, however? We wanted to find out how much, so I'm assuming that's mass in grams, of lithium carbonate are we going to produce with these relative numbers of products. Well, we need to look at the ratios of the coefficients of our desired quantity with our reactants. We see that for every 1 mole of carbon dioxide, we're going to produce 1 mole of lithium carbonate. We know how many moles of carbon dioxide we're consuming. We are consuming 0.34 moles. So let me switch to, let's see, a nice magenta color. We're going to have 0.34 moles of carbon dioxide, which means, since it's a 1-to-1 ratio, we're going to produce 0.34 moles of lithium carbonate. Whoops, I've got a 2 there. Lithium carbonate. Finally, we want to get the amount of lithium carbonate in grams. Remember that this question is asking for the amount in grams, mass in grams. And to get that number, we're just going to multiply our number of moles by the molar mass of lithium carbonate. And to save a little time, I'm just going to tell you that the molar mass of lithium carbonate is 73.89 grams per mole to 4 significant figures. To get the amount in grams of lithium carbonate which we produce, we're just going to multiply 0.34 moles by 73.89 grams per mole. Take a look at the units. Something nice happens. Our moles cancels. We're left with grams. Good, that's the unit we want. And to two significant figures, this is going to equal a nice clean 25 grams of lithium carbonate. Now, let's say you didn't realize you had to multiply. Let's say you had this number of moles, you had this molar mass, you've gotten that far, but you didn't know what to do to finish up that calculation. Well, there are really two options. You can either divide one number by the other or multiply. And you can use the units to figure out what you actually want to do. If we divided, say we divided moles by grams per mole, by the molar mass, our units would be, let's see, moles squared over grams, and that's kind of scary. We don't want those units. Those are weird. I don't know what quantity that would give us. We want grams, and so we multiply and we get the right unit. And whenever you get the right unit, you might be wrong, but you're probably right. If you get the wrong units, you're definitely wrong. So that's a nice little check you can do. But finally, let's just review the steps you use to solve a stoichiometric problem, to figure out how much product or how much of anything you have given some initial information about the conditions of the chemical reaction. First, you're going to balance the chemical equation. Let's see, did we do that? Yeah, I think I did that for you. Yep, this chemical equation is balanced. Check. We're going to convert the information we have from masses to moles. We did that right here. We figured out the number of moles of lithium hydroxide we had and the number of moles of carbon dioxide. So that was our second step. We're going to find the limiting reactant, and we did that using the mole ratio. And this is a nice little method I suggest. We set up this proportion. We need 2 times the amount of lithium hydroxide as we do carbon dioxide. If this number is greater, if this actual ratio of moles is greater than your stoichiometric mole ratio, then you're going to have too much of the stuff on the top. If it's less than your ideal stoichiometric mole ratio, then you're going to have too much on the stuff on the bottom, and the other reactant is going to be your limiting reactant. So in this case, if this number had been less than 2, lithium hydroxide would have been our limiting reactant, and we would have had too much carbon dioxide. So we did that. We found our desired quantity. We figured out the ratio between lithium carbonate and carbon dioxide. And we figured out the number of moles of lithium carbonate which we produce. Finally, we wanted the mass in grams of lithium carbonate, so we just converted moles of lithium carbonate to grams of lithium carbonate. And that's what you're generally going to do in any stoichiometric problem.